Patty Simpson with Simpson Math. In this series of videos, we're discussing the parent functions. And in this particular video, we're going to look at the parent function of a quadratic equation. So first, let's just remind ourselves what a function is. A function is, for every input that we have, it's a relationship between our inputs and our outputs, where for every input that we have a unique output, or one output. Exactly one output. And we're going to look at the parent function of the quadratic, which is the simplest form of that quadratic function. So let's just look for a minute at some various quadratic functions. So if I have something, here's a family member, something like this, where I have 3x plus x minus 2. Or maybe in function notation, remember we can replace that y with this f of x, our output here. And here's another example of a quadratic function. And then, so these are examples of that quadratic function. And notice in each one of these that we have the highest degree on our function here is a 2. And the same thing is true here. If we were to multiply that out, our highest degree on this x would also be 2. So these are just some family members. And maybe we look at it more in general so that we have something like this, where we have again that quadratic function where we have the 2 are squared on our x value. And I'm just going to put in some numbers here for my b and c. So, and my a, if I make my a 1 and my b and c both zeros in there, then I end up with, 1 times x squared is just x squared, plus 0 just gives me the x squared. And this is the simplest form of our quadratic function. Or we say it's the parent of the quadratic function. There it is. With the y, and we can replace that y with f of x, that function notation. Both of those are the parent function of our quadratic function. Now we're going to graph this quadratic function. And before I graph the quadratic function, I want to think for a minute about our x values. Is there a number that I put in for x where I don't get out a real number for my y? Is there any real number that I put in for x that I don't get out a real number for y? So let's just put in some values for x for a minute and check that out. So how about 0? Let's try 0 for x. If I put in 0 for x, so 0 squared is just equal to 0. That's a real number. So my y value is a real number when I put in 0 for x.
What about a negative?
What about a negative? Let's try a negative. How about I put in, say, a negative 2? So I have negative 2 squared, putting in negative 2 for x. Negative 2 squared is 4. That's a real number.
What about an irrational, like root 2?
We can put in an irrational number, like the square root of 2. If I put in the square root of 2, and square that, well, the square root of 2 times the square root of 2 is just equal to 2. That's a real number. So it turns out that I can put in any x value in for x, any real number in for x, and I'm going to get out a real number for y as well. So we say that the domain of this quadratic function is any real number. So I'm going to show you some fancy notation that just says exactly that. We're going to have a whole nother lecture on domain and range later, but this just says x such that x is an element of the real number. So in other words, x can be anything. And there it is in set builder notation, or in interval notation, our x can go anywhere from negative infinity to positive infinity. So I can put in any number I want to in for x and get out a real y value, any real number in for x, and I get out a real y value. So I'm going to pick these 5 values to put in for my x. I'm going to put in negative 2, negative 1, 0, 1, and 2. So if I put in negative 2 in for x, negative 2 squared is equal to
4.
If I put in -1 for x, -1 squared is equal to,
1.
if I put in 0 squared, I get out.
0.
If I put in 1 for x, I get out.
1.
And if I put in 2 for x, I get out.
2 times 2 is 4.
Perfect. So these 5 points are points on that parent function of the quadratic function. So here I'm going to graph these 5 points, -4, 2. Remember, we walk first and then we climb. 1, 2, 3, 4. I'm going to go over -1, 1, -1, up 1. There's a point at 0, 0. Notice this point is on both my x-axis and my y-axis. We say that this is the x-intercept because it's on that x-axis, and it's also the y-intercept because it's also on the y-axis. There's a point at 1, 1 and a point at 2, 4. And we said that the x can be any real number or any value between -infinity and infinity. So it's not just at those points, but it's everywhere in between as well. So I'm going to connect these dots to show that there are values in between there as well. And it continues to go. If I put in 3, I'm going to get out 9. If I put in 5, I'm going to get out, or -3, I'm going to get out 9. If I put in -5, I'm going to get out -25. I can keep doing that forever and ever. So I'm just going to show that by putting these arrows on the end of my graph to show that it goes on forever and ever. And there is the parent function of our quadratic function that we have graphed. So I could label the points here and tell you, hey, that's an x-intercept and this is my y-intercept. I could label each of those points. And remember when we did function notation and we put in values like this, where my x value is 2, and I get out, well, I can look on my graph now where x is 2 and look and see here, there's a point there at 2, 4. So when I put in 2, I get out 4. Or let's say I said my f of x, or my output value, is 1. Well, then what is my x when my output value is 1? So this is my y. So now I'm looking at my y. When my y is 1, notice that I have 2 points there where y is 1. So my x is either -1, -1, 1, or my x is 1. So there's 2 different values there for when my for when my output is a +1. So there's the quadratic function. So when we graph our parent, we're just going to use those 5 points. Thanks for watching.